everybody. I'm here. Who's feeling kind of run over by the semester right now? All right, I'm with you. Jeez. Boy, howdy. Anyway. So, midterm 2, today, baby's sick. I'm sick. Watching her, trying to get Project 2C out. Oh my goodness, what a life. Anyway, I'll try and be friendly and keep you guys from being broken by 61B. Let me know if you're like, ow, a lot, and I'll try and figure out something useful. Anyway, so midterm 2 scores, they'll be out shortly. It's basically done. I just want to do some sanity checking after class. So sorry for the delay. I caught a small grading error where people got 0 points for when they should have got some. We had to go back through about 400 or 500 questions. I either found that Sunday or Monday. I actually don't remember. That took a little while to fix, and now it's done. Project 2C will be out later tonight. It is smaller than 2A and 2B in terms of total effort required. Certainly less than 2A. And 2B was easier because you had me doing the walkthrough for part of it. So 2C, I'd say, is going to be shorter than those projects, but it'll take some time to figure out how things work because you're going to be interacting with a gigantic code base. You're only going to have to edit a few little pieces of it, but understanding how to get started, I'm warning you in advance, will probably take, even just setting it up so you can compile your file will probably take 20 minutes or so. Just lots of little things. But don't worry, there's directions, and hopefully it'll be fine. In terms of the grades for Project 2A and 2B, I will figure out a plan by this weekend. The TLDR is that I want to get you points, partial credit points, in a way that is most helpful and least stressful. I had an original plan, but then somebody came up with another plan. I wanted to think carefully about whether theirs is better. And it just didn't feel as time critical. Now, for some reason, because we didn't get grades out by the PNP deadline, a student wrote to me basically and said, I missed the PNP deadline. I really wish I'd had that grade beforehand. So if that's you, please let me know, and I will try and help you out. Any questions about midterm 2, Project 2C, or anything else? Yeah. Project 2AB, please. Yeah, so if you had something where the grader gave you 0 points because it totally crashed, don't worry. Like the original scores when we ran everybody's, there was maybe 1% of people where things went really weird, so we had to rerun those. And you haven't seen the rerun yet, so don't panic if you have 0 points because something failed to run. Other thoughts or questions? All right. So today we're talking about Quicksort. That's one of my very favorite sorts in the whole world, but we can't talk about it yet because we need to talk a little bit more about Insertion Sort. I wasn't really happy with the way we ended last lecture, so let's redo how we ended. So reminder, Insertion Sort. It is a way of sorting items as follows. We have all of these letters, in this case the letters S-O-R-T-E-X-E-A-M-P-L-E, and I want to sort them. So the way Insertion Sort works is S is originally the traveler and pushes its way to the left until it finds its appropriate place. So for example, O is less than S, so on this step it went to the left. R pushed its way past S, T did not move. However, E, which is smaller than O, R, S, and T, had to go all the way to the front. Now we already did this question, but just so you have a moment to kind of put back in your brain what Insertion Sort is, I would like you to try and solve this problem again. I'm only going to give you 40 seconds just to warm up. All right. So as I said last time, we already actually did this, but just as a reminder, the best runtime, in the best case, the runtime is theta n. And so overall, I could say that the runtime is bounded below by n. So if the best is theta n, the overall runtime in all cases is omega n. And that would be the case where it's just green letters on the diagonal. So that would be, for example, A, B, C, D, E, F, G, H, I, J. Each letter would look to its left, see that that item is already smaller, and would do nothing. In that case, that takes n time for all those items to be the traveler, look, and be done. And then in the worst case, everybody shoves their way to the front. That's the area of a triangle. That's n squared. So any questions about that? Just a reminder of what Insertion Sort is. Okay. So here's the other question that we did not do, that I skipped, but I want to do it because I think it's an interesting one. All right. So let's say we read 1 million integers from a file, and then and it's in an array. It's all in one big array. And then we merge sort them. So after merge sorting, they'll be in order, and that merge sort will take how long? So how long is this step? N log n. Okay, good. Now what I'm going to do is find one integer, and I'm going to randomly change it. So I pick some arbitrary integer, maybe the one in the middle, and I change it to 6. I don't know, just one of them. Now I'm going to sort again. So I want to know what would be the fastest algorithm for sorting out of these 4 choices: selection sort, heap sort, merge sort, or insertion sort, which I'll remind you have worst case runtimes of n squared, n log n, and n squared, respectively. I'm going to let you keep thinking. I'm just going to write some notes. All right. So I'm going to spoil it here. So if you paid close attention to the end of last lecture, I did spoil this already. But somewhat surprisingly, the answer is not merge sort or heap sort, but in fact is insertion sort. And the reason is that in insertion sort, if you just change just one item, then the worst case is going to be linear. That is, it is going to, that item, when it's the traveler, it's going to take however many steps it needs to get to its new appropriate place. And that number will just happen to be the same as the number of inversions. Now, you can actually generalize that property a little and say that so this is an example where I have just one letter out of place. And you could see that in this specific case, where only one item is out of place, then it's just going to travel, and the longest it can go along a line is going to be, well, a line, linear, right? Now, this is another example showing that if we have a small number of items that are all just slightly out of place, again, the amount of work is very little. Okay? And if you spend a little more time, you can actually show that the number of swaps that insertion sort does will be will be equal to the number of inversions. So any questions about this? Now, one thing I didn't tell you is why merge sort and heap sort are worse. But if you play around with them, you'll realize that merge sort and heap sort end up spending both n log n time for this example. We didn't show that, though. Okay. So, in terms of the so insertion sort, like why it matters, because there was a great question in lecture before, which was, why are we learning all these different sorts? Are they all useful at some points? And so insertion sort, it turns out, is actually useful in practice. So you could show by study guide problems, not yet out, I think, or maybe they're up now. Let's find out. I think they're up, maybe. Let's check. Okay. Yeah, back up to date. All right, cool. Anyway, you could show that the insertion sort, it's one exchange per inversion. So you do one swap per every inversion. So the overall runtime would be n plus k. So n is the traveler, each of those items being the traveler, and the k is the total number of items that get pushed aside. So if we define an almost sorted array as one in which the number of inversions is less than or equal to cn for some c, that is, it has a linear or better number of inversions, then insertion sort will do really well. Somewhat strangely, insertion sort is also really fast on small arrays. So if you have an array of 15 items or fewer, insertion sort will be faster than merge sort or heap sort or whatever else, though that's a bit of an empirical observation. That's not something you can easily show theoretically, because our runtime analyses, we're thinking about asymptotics. This is not an asymptotic analysis. Why? Small n, exactly. So the rough idea, though, is that these divide and conquer algorithms like merge sort, they spend too much dividing and not enough time doing conquering. So actually, if you look at real-world implementations of merge sort or Insertion or Quicksort or whatever else, what they'll do is when they break down, once the piece of the array that needs to be sorted is less than 15, they will actually switch to Insertion Sort. So if we click here, we can actually look at the code for merge sort in Java. So there's a method called arrays.sort, which sorts arrays. And once AirBears finds it, or not, oh boy, okay. Now is it AirBears' fault? I think it's grepcode's fault. It's too slow. But anyway, you can go look later, sorry. Danger of live demos. But if you look at the merge sort code in Java, it says, if the length of what I'm looking at is less than 15, switch to Insertion Sort. It's kind of a hack, but it works. All right, any questions about Insertion Sort or our basic sorts? All right, so now I'm going to talk about my buddy Quicksort next. Summary of what we've got so far. So I'm going to give you a little backstory. I like how Quicksort was invented. It's a weird story. It was invented by a guy who was not really a computer scientist for strange reasons. To get to the story, I would like to observe that the different sorts we've seen all have a different key idea. Selection sort, it's all about finding the smallest item and putting it at the front. And we saw the heap sort variant, which uses a priority queue in order to keep track of the largest, or in our case, the largest, or it could be, you could either use a max PQ or a min PQ, either way, but they'd both be a type of selection sort. It's about finding the most extreme element and putting it on the end. Then there's merge sort, which is based on the idea of merging. And insertion sort, it's based on the idea of trying to figure out where to insert the current item. Now, Quicksort is based on a fourth, totally different approach to sorting, and it's something called partitioning. And this was invented by a guy who was eventually knighted for computer science. It's a thing you can do these days, named Tony Hoare. And in 1960, he was a novice programmer who was facing the following problem. So he was studying in Russia during the Cold War era, and he was trying to build, at the very outset of early days of computer science, an automated translation algorithm. And so basically, he wanted to take a phrase like "the cat wore a beautiful hat." There are n words here, where n is 1, 2, 3, 4, 5, 6. Here's the cat. And he also had a dictionary of English words that would map to their appropriate Russian word. So cat, I mean, I don't speak Russian, but hey, this is some cutesy version of cat, koshka. But yeah. And so the cat wore a beautiful hat. The crude translation might be this. It's not necessarily grammatical, but it just says for each word, let's find the best approximation and then make a bad translation. You know, it's 1960, so we're not going to need too many. It's good enough, maybe. All right. So that's the goal. And so how would you do that? Like, if you had to do this, what would you do? Like, how would you maybe approach this problem? So iterate through the words and then do what? What's this thing going to be, maybe? I don't know, maybe it's a hash map. Yeah, you have a hash map, and you just say, give me the word cat. There's a lot of different ways you could do it. But this is 1960, and Tony didn't have all these fancy libraries that you might have today. So another approach you could do, if you don't have hash maps, is maybe you could try and binary search. So if the dictionary is sorted, then you could do a binary search of this and say, hey, where's the? And you would binary search, and if it's there, good, and if it's not, then you don't return anything. You binary search and find cat, and so forth. And each of those binary searches takes log d time, and since you have n words, it would be n log d. This is something else you could try. Now, there was one major constraint that made this not a good approach, which is that at the time, array accesses were not constant time. What? Well, the thing is, then there wasn't memory as we know it now. There wasn't RAM where I could just say, I want item number 88 or whatever. Instead, all of the data was stored on a piece of physical tape. And if you wanted to go from beautiful to cat, you would actually wind the tape, like over, and into the appropriate location. And so binary search means you have to wind the tape really far and then go halfway back and so forth. And it turns out that binary search is no longer fast if you're doing binary search of a tape. Okay. Anybody here has used a tape club? So, yeah. Anybody else? No? They're so fun. Anyway, all right. So data was stored on tape at the time, couldn't do it. Now what he did have was a small amount of memory where the dictionary, while it would not fit in the computer's memory, the sentence would at least. And so his approach was, okay, I'm going to take just the sentence that I have and I'm going to sort it. So I'm going to sort the cat wore a beautiful hat. And then I'm going to go through the tape one time. And because the words in the sentence are now sorted, we know that we're going to pick the words up in the appropriate order. So we only have to scan the tape just one time. So the total amount of time it would take would be in log n for some kind, say he merge sorted or whatever, the sentence, and then it would take d time to go through the whole tape. Now the problem Tony faced was that he had to sort this array of words here, because he has a small amount of array memory and not enough memory to store this all in. He doesn't have enough RAM to store this, so he has to rely on tape. And he needs some way to sort just the sentence, but he doesn't have Google, so he can't go to Stack Overflow. He doesn't have libraries that do sorting. So somehow he decided, if you read the original story where he talks about this, his first idea was something known as bubble sort, which we won't teach. It's a very basic sort. And then somehow the second sort he thought of was this, which is a very strange idea. So the core idea in what Tony came up with back in 1960 is that we are going to partition our array. So what does that mean? Well, I have an array which is 5, 550, 10, 4, 10, 9, 330. And I'm going to pick an item, which I'll call the pivot, and then I'm going to rearrange the items so that X moves to some new location, and then all the entries to the left will be guaranteed to be less than or equal to X, and all the entries on the right are greater than or equal to X. So for example, we have A, B, C, and D, and of these, some of them are valid partitions. So what I would like you to do to understand the idea of partitioning is to figure out which of these 4 partitions are valid. Now, this is not a yellkey question, so you just have to figure it out and decide which ones you think are valid partitions. This is my initial array. Yeah, so J, by the way, is the location where X ends up. It starts out in position I. J is its destination. So don't worry about how one does this. All I want you to do is tell me which results are valid. Is this a valid partition on 10? Okay, so it turns out only one of them is problematic. A, B, and C are all valid partitions. D is the only problematic one because 4 ends up on the right-hand side. Any questions? All right, so that's partitioning. So we haven't come up with an algorithm to actually partition yet, but we know that such a thing exists. Okay, so all 3 of these are valid partitions. All right. So this is a question for you now. So this is the kind of question that might come up at technical job interviews. They kind of happen sometimes. So given an array of colors where the 0th element is white and all the rest of the items are red or blue, or if you want numbers, you can think of the red ones as things that are less than the white element and blue as those that are greater, I want you to rearrange the array so that all the red squares are to the left of the white one and all the blue squares are to the right. And you have to do this in time, and there's no space requirement. And you don't have to worry about the relative order. So there's 2 valid partitionings here. So try and come up with some technique for doing this. I'll give you guys, again, a minute and a half or so. So you can make more arrays or whatever you want. Anything you want to do. All right. I'm gonna take a couple or maybe one suggestion. So anybody want to give me an algorithm? Preferably somebody who I don't usually hear from, but whoever. Thoughts? Yeah, go ahead. Okay, so let's see. So if it's smaller, move it to the front. So we'll take 4 and move it to the front. Okay. Then what? Oh, you skip it? Okay, sounds good. So we can kind of move that around, over and over. And so obviously if it's an array, you'll have to do some other stuff, but yeah, you got the basic idea. Great, all right, I like that approach. So basically scan through the list. I'll write it out in words. It's a different one than I'm used to hearing. I like that one. That was cool. Okay. So this approach was, if you missed it in the animation, it's scan from the right edge of the list. If anything is smaller, stick it in the leftmost position. Skip larger items. Okay. Yep. And if you had, say, a double-ended queue, that's a very natural use for a double-ended queue. Maybe I'll replace palindrome with this next semester. Because I always found palindrome to be kind of a somewhat lame use of a queue, because you don't have to. But here it's so convenient. Anyway, cool. I like that. All right. Anybody got another one? Yeah. Oh, insert 6 as a BST into the root. Okay. Oh, interesting. Okay, so I can't do that usually visually, so I'm gonna write it down. This is a funny suggestion, or I mean, curious suggestion. So insert 6 into a BST, then what? Keep going. Then what? Then 8, then 3, then ... then 4. Then what do you do? So how does this give you the partition version, though? Oh, all the small items are on the left. All the large items are on the right. That's also a very exotic solution. Interesting. Cool. You guys are like having, I like these very strange answers. They're interesting. All right. Something like that should work for an interesting reason. Had you seen something similar to that before, out of curiosity? It's very interesting. Okay. I'll circle back to that idea. All right. I'll give you the third approach. This is, I think your approach is actually simpler, by the way, but this was my old simplest approach, which is given an array, okay, you know the story, what we could do is create another array, and then we'll just scan through the array 3 times. The first time we scan through, we grab all the red items, and we do 3, 1, 2, 4. Then we scan a second time and find the white item. Okay, there it is. It's at the front. I mean, it's kind of trivial, but this generalizes to multiple white items. So then we'll add the white item. Then we scan and do the blue scan, and then we do 8, 7. I don't know. They're both pretty simple. Okay. So that's going to be the approach that I will use. But the point here is there's many ways of partitioning. And this is not the way that Tony did it. His was very strange. It involved, your scanning idea you proposed where you go from the right end and go over. He had 2 pointers that come towards each other in the middle. And we'll talk about that approach at some future date, but not today. Okay, so everybody happy that partitioning is a thing and it's something that you can actually solve in various ways? All right. So that brings us to Quicksort. We know how to partition, so how do we sort using it? All right. So here is an array, and if I partition on 5, I end up with that array there. Now, you'll notice that is not sorted, right? Yes? How did I pick green to be the front? Yeah, so in this case, I did the 3 scan approach. Everything that is smaller is to the left. Everything that is larger is to the right. So there are all of the movements that happen, and we don't really need to think about code. We have the basic idea. Now, question, how would we actually do this? This is not sorted. It's different, but it's not sorted. So the question is, how do we use it for sorting? So I'm going to make some observations. One is that 5 is in its place. That is, it is exactly where it'd be if the whole entire array were sorted. These are all of the items that are less than 5, and these are all the items that are greater than 5. So 5's in the appropriate place. Okay? There's no way that 5 ever needs to move again. By definition, like you could think of this array as it's sorted with respect to 5. The other is that at this point, there's no reason that these two halves of the world need to interact anymore. On the left, we have 3, 2, 1, 4. There's no way that any of these are going to move to the other side of 5. So 5 is not only sorted. Like, you could think of the array, only the 5 is sorted. And it breaks the problem into two halves in this case. There's all the numbers that are smaller than 5, all those greater. And so we could, in this case, recursively sort the other two halves. We could do it by merge sorting the left and merge sorting the right. We could do insertion sort on the left, insertion sort the right. Or we could do the same thing where we partition on both sides. And every time you partition, how many items are going to be guaranteed to end up in their place? 1. So when you partition on an item, it ends up in its place. And so just by definition, if you partition on all 8 items, by the end of that process, the whole array will be sorted. But you'd never have to go that far. So in this case, we could think about it as there's two different subproblems to solve. There's 3, 2, 1, 4, and 5 is this wall that nothing will ever cross again. So if I partition on 3, and I do that 3 scan approach, which items are less than 3? 1 and 2. And if we're doing 3 scan, I'm just going to copy them directly over, so they end up in the same relative order. So here's 2, 1. That's just the approach I used. But again, you can do it however other way you want. So we have 2, 1, 3, 4, 5. And here we have 5, 6, 7, 8. And you can see we're now closer to being sorted. Okay? So let's see a full demo. All right. Okay, this time I feel safe. It's not on grep code. Okay. So this is how we go about quick sorting in items. So we start by partitioning. This is one variant of quicksort. There's innumerable, like thousands and thousands of versions. But I'm going to say my version of quicksort is use the left item as a pivot or as the thing to partition on, and then that's just the rule. This is arbitrary. You don't have to do that. You could say rightmost, middle item, third item, whatever you want. Okay, so I'm going to partition on the leftmost item just because I picked that. And at this point, if I partition on 32, we could think of all these items as the red ones and the blue one, and 41 as the blue item. So after partitioning, no surprise, 32 ends up in its place. Then I have 2 subproblems. I will now quick sort the left and the right half. So what is quick sorting? How is it defined? Well, it's defined as partitioning on the leftmost item and then quick sorting both halves. I don't show the base case explicitly on the slide. So if we if we quick sort the left half, who will be the new pivot? 15, right? So I didn't show all the steps, but I do have them. But if you trust that it's a recursive algorithm that actually works, then there's no surprises here. All of these things will end up being in its place. So this is basically the call of partition, or the tree of partition calls. 32, the next pivot will be 15. 15 will end up having 2 and 17. 17 will have this child, 19, and so forth. And then I'll quick sort the right half. Now, if you want, there's the longer version of the demo that I'm not going to do here. If you don't really trust the recursion, that's fine. But this version will go through it in detail. But I don't want to do it in lecture because it's a little tedious. Okay? And there's not actually anything new here. Okay? If you trust that recursion works, you don't have to do this demo. But I still think it's helpful to see. All right. So any questions about this? So try this out again later if you'd like. But you end up with this table of partition calls that basically says, when I partitioned on 17, I guess I'll just show you that because I think it's an interesting point. When this 17, here we go. 19, okay, going back up 1. All right, so when this 17 happens, it ends up in this position, and you'll see it has no left subproblem. It only has a right subproblem. What items are in its right subproblem? 19, 26, 17, and 17. So that's why I'm putting an X here, just for notational reasons. So that by the end, this is the breakdown of all the subproblems that end up happening. Okay? Now, your recommendation earlier of using a BST is very closely related to this. You'll notice that this object here is a binary search tree of all the items. Here's 2, 15, 17, 17. Oh, sorry, I missed one. 17, 17, 17, 19, 26, 32, 41. So there's actually a very deep connection between binary search trees and quicksort. All right. So, quicksort, why does it name this? Selection sort is about selection. Heap sort's about heaps. Insertion sort's about inserting. So why does Tony Hoare get to call this quicksort? Well, he just did. Now, bizarrely, even though he was not a trained computer scientist, and he basically just made this thing up and named it quicksort, it is actually the fastest sort. Okay, so I don't know. So he was just very lucky that the name was correct. Now, how fast is quicksort? Well, that's going to take some time. We're going to have to be careful about that if we want to do an asymptotic analysis. And it is one of the most interesting asymptotic analysis that we will do. So in terms of how we're... Actually, any questions about where we are so far before we start jumping into asymptotics? Merge sort, yeah. So why do they use altered merge sort? So we will talk about that early next week. Actually, Java uses quicksort in some circumstances and merge sort in other circumstances. Speed's not everything is the short answer. There's another property known as stability that is desired in sorts. All right. So let's talk about how you actually analyze this thing. So this is just an observation that has been made in the world that is empirically the fastest sort. It's also, we'll show that it's also, well, no, I'm not going to spoil it. Never mind. But some of you may know where I was going to go with that. Anyway, so to analyze this, we know that partitioning costs theta k time, where k is the number of active elements, the number of green elements in your subproblem. And we saw that in our earlier interview question. That was how we, when you guys came up with an algorithm, the cost to partition a set of elements is how many active things you're thinking about. Now, the interesting twist and the thing that makes Quicksort so fun is that the runtime depends on where the pivot ends up. If the pivot's in the middle, that's good. If it ends up on one of the ends, that's bad. Okay? So let's talk about different analyses of Quicksort. This is the very best thing that can happen to you in Quicksort. You pick a pivot, and it ends up in the very middle, splitting your problem neatly down the middle so that you have two subprime problems of half the size. Now then those two pivots, in the best possible case, end up in their respective middles. And the four new pivots end up being in their best possible cases. And at this point, we're done. Okay? So at this point, there's only size 1 problem, so we can call it a day. All right. So what's this runtime going to be? What do you think? I'll give you guys 45-ish, maybe a minute, to try and convince yourself what the runtime ought to be for this best case. So my hint is that each partition costs theta k, where k is the number of active elements. So a hint is think about the number of work, or the amount of work per level, and the number of levels. Okay, so it turns out, if we think about how much work is done at each level, at the top level, it costs us about n units of work. That is, I have n items, I got to look at all of them to do my partitioning. Okay. I don't have an exact cost model. But I hope the intuition is clear. At the next level, I have two subproblems that are about n over 2. Now, it's not exactly n over 2 because we lost one item that's already done. So yes, there's a -1 here, but it's about n, right? So at that level, the total amount of work is also about n. At the next level, it is also about n, and so forth. And you go down the whole tree. And yes, it's just a little tiny bit less at each level, but the argument holds that the overall runtime then is going to be, because each work does about n work, and how many levels are there if we're cutting in half every time? Log base 2 of n, so the overall runtime would be n log n. Now this is a little bit of a hand-wavy proof, but I will leave it to, 170 or something to go into more detail. I mean, the only thing we have not dealt with is the technical issue that, yes, we're losing one little item, but we can get rid of that if we want to just talk about big O. We can bound above by saying the work at each level is certainly big O of n. And if you want, you can sit down and show that it's actually also theta of n. Okay. All right. Any questions about that? So it's very similar to merge sort. All right. Here's the worst case. So in the worst case, the pivot just ends up where you started. So this would be, for example, I have an array that's 1, 2, 3, 4, 5, 6, 7. I don't know, something like that. So what would be the runtime for this case? So remember that partitioning costs k, where k is the number of active elements. All right, suggestions? What do you think? N squared, I heard someone say. Yes, it's n squared. So why is that? Well, the overall runtime, think about it this way. This partition, how many elements do we need to look at? 6. Or like the runtime, it's proportional. It'll be about 6-ish, right? But at the next level, we've lost one item. So that's going to be 5 to do that partition. And 4, then 3, then 2, then 1. So this is just the sum of the numbers 1 through 6. Now, you could do a more detailed analysis where you pick a specific cost model, like array accesses or copied items or whatever it may be, but you'll get the same answer, that the runtime has stayed n squared. Yes? This could be either way. Depends on this example I gave is, let's see, if I did 1, 2, 3, 4, 5, 6, you'd end up with this here. Yeah. Because if you do 1, 2, 3, 4, 5, 6, you partition, and all these items just stay where they are. All right. So theoretically then, in the best case, quicksort is n log n. That's where you land right in the middle. In the worst case, it's n squared. Compared to merge sort, which is always n log n, it seems a little strange to say that quicksort's better. I just said it's empirically observed, but we've just theoretically proven that empirical observation wrong in some ways, right? You could argue. N log n versus n squared is a tremendously big deal. If you use an n squared sort, you're doing something bad. However, the reason that it actually works in practice is that on average it's n log n. So quicksort, yes, there are technically arrays that will give it an n squared runtime, but on average it'll be n log n. Now, if you really, really want to go through and prove this about the average case, you need probability theory and calculus, but I hope that with some intuition, I can maybe convince you that this is likely true. Okay, so I'm not going to prove the n log n on average, but I am going to try and convince you of this. Now, before I even get there, if I tell you that an algorithm is n log n on average, but there's still an n squared worst case, that is incredibly dangerous, right? That means there are some arrays that will break your quicksort. Nonetheless, it is something that we live with, and I'll philosophize a little bit about that in a bit. So, okay, so far I've shown that quicksort, or you guys have shown that quicksort is n log n in the best case and n squared in the worst case. So now I'm going to give you not a full proof, because again, we need probability theory in order to talk about the average case here, but I'm going to give you a hand-wavy kind of like intuitive proof for the n log n. So here's one argument, is the 10% case. So let's suppose the pivot always ends up at least 10% from either edge. So it's not going to land exactly in the middle. It's just going to end up, I don't know, like 10% along the way. Anywhere in that 10% range. It could actually be further away, but it's at least 10% from the edge. It's not over here. Okay, that's a decent chance, I guess. And let's say then, so at that point we'd have two subproblems of size n over 10 and roughly 9n over 10. Okay, so it happens again. Each of those pivots end up around 10% over. So we end up with a subproblem of size n over 100, 9n over 100, 9n over 100, and 81n over 100, modulo the fact that we're losing a few items along the way. And so the total amount of work at each level, you'll see, is big O of n, because we add up all the work at those levels. So if you think about what this tree looks like, this left branch is going to run out of items sooner, right? Like here we're already done. You can think about that. But the right branch of the tree will keep going. So the overall amount of work is certainly going to be big O of n. It's not actually going to be equal to n because these left branches run out sooner. So the runtime in that case would be n times h, big O of n times h. And how many levels are there? So the right branch is going to be the longest branch. So how far do we go here? Any idea? So it turns out that instead of log base 2, maybe you can get this sense from, it seems like it ought to be something like this, and you can show that it is. The height is going to be log of 10/9 of n, which is still just log n. Okay? So overall, in this argument, like this is the case that's saying, like, even if you're not so lucky that you always end up in the middle, even if you're just always within 10%, then it's n log n. And you can actually generalize this argument to any percentage. You could say the 0.1% case. As long as it's at least in the last 99.9%, I'm good. Okay. Any questions about this argument? This is only meant to build intuition. This is not going to win you any awards. All right. So the punchline is that even if you're unlucky enough to have a pivot that never lands in the middle, but at least always lands 10% from the edge, it's still n log n. Okay? Here's another one, is that quicksort is BST sort. Okay? So we saw heap sort, which is throw all your items in a heap and then remove them. Well, it turns out that quicksort is the same thing as put all your items in a BST and then do an in-order traversal. So here are the partitions we did earlier, and this relates to the idea that you had earlier, that if we have 5, 3, 2, 1, 7, 8, 4, 6, when I partition on this, I end up with 5 in the middle. Now on the BST side, that's the same thing as saying that 5 is the root of my BST. And then on the left, the next pivots I have are 3 and 7. So, actually, sorry, the next pivot I have is 3, and it has a left and right subproblem. And so the next pivot that pops up is 2, and then you can go on and say, oh, we have one last size 1 problem, which is here, and on the right, we would also have a 7 over here, okay? I have my 4. Okay, I don't know why it appeared in that order. And then we have 6. All right. So it turns out that if you think about the actual comparisons, and there's a really nice study guide problem if you have time at some point, I don't know, in some future weekend before the final, where you can actually sit down and write down every single comparison that happens if you insert into a BST versus every comparison that happens whenever you partition. So for example, whenever we do this partitioning operation, we have to compare everything to 5. And when we build this BST, because we've added all these items, they've all been compared to 5. Okay? Actually, here, I guess I'll ask a question to maybe make this make a little more sense. Sorry, I went on a kind of a weird track with this. But here's 7, 8, 6. So when I partition this little subarray, which items get compared against 7? 8 and 6. Okay? If I have a BST where the root is 7, and I insert 8 and 6, which items get compared against 7? Both of them. Do 6 and 8 get compared against each other when partitioning? No. Did they get compared against each other when this BST is built? No. So that's, again, kind of a hand-wavy argument. But it turns out that quicksort, I mean, it is BST sort. The exact same comparisons get made. So if you write down the compare to calls that are called, they are the same. And you may recall that a randomly created BST has a height, which is logarithmic, and that the overall time to construct that tree is therefore n log n. So if you trusted the thing I just stated as fact, never proved, that a BST, when randomly created, is n log n to create, then you will also agree that quicksort is n log n. Now, this is a pretty deep and crazy topic. I mean, I hope that quicksort makes sense, but this will take some digesting for most of you. Yeah? Yes. So if it makes a spindly BST, it takes n squared time. And an example of that would be the numbers 1, 2, 3, 4, 5, 6, 7, 8. So that BST would be spindly, and also the partitioning would be slow. So exactly right. Yes. Yeah, so could you make an LLRB sort or just a 2-3 tree sort or whatever else? And you can, and that sort's called tree sort, and it no longer has the nice elegance of this algorithm. So if you tried to do it in raw array format, your brain would explode. It just wouldn't feel good. Like BST sort, it just happens to feel good even as a native sorting algorithm. But LLRB sort is just, it's mind-blowing and weird. And just, it feels arbitrary, all the operations. Yeah. Yes. So how do we fix that problem? How do we avoid that worst-case runtime? Could we just always use the median as a pivot? Yes. And so we'll talk about strategies for mitigating the n squared towards the end of this lecture, which is coming quite soon. All right. So you can run empirical studies, by the way, where you say, okay, well, I mean, I know that the best case is n log n, the worst case is n squared, on average it'll be n log n, but what actually happens with real data? So this is an empirical histogram drawn, I think, originally from Bob Sedgwick's thesis, but I grabbed it from this site. And you can show that the mean number of compares that are needed to complete quicksort are 2 in natural log n, which, by the way, is closely related to the height of a random binary search tree. And you can also find the standard deviation, which is 0.6482 n. And what I mean by standard deviation is if I make a bunch of random arrays of 1,000 items, this is the distribution of number of compares needed to sort them. So if I have 10,000 items, so if I have 1,000 items, then on average it'll take somewhere around 12,000 compares to sort them. Sometimes it only takes 11,000. Occasionally it takes 15,000. But what it never takes is about 1 million. This distribution is skewed so heavily towards this 12,000, and the really tiny number of permutations that involve n-squared operations is very, very, very rare, if drawn from a hat randomly. All right. So lots of arrays that take around 12,000 compares, but some of them take more. All right. So the chance of taking 1,000,000-ish compares is close to 0. So then, summarizing the performance of Quicksort. In the worst case, it's n squared, but in the totally random array, it's n log n. And that's with extremely high probability. Now, we'll come back to that in a second, but first I want to note, you might say, why is Quicksort faster than merge sort? Like, how have we shown that? Well, we can't. There's no really good theoretical analysis I know of. Knuth, he kind of tries it in TAOCP, but it's a little arcane, and it makes just a lot of assumptions. It's more of an empirical fact than something that has been proven. Okay. So to summarize, before we get a little taste of mitigating n-squared behavior, though we're going to mostly push it to Monday, we have this new idea, this idea of partitioning. And it's a totally different way of approaching the sorting problem that has this really great property that it's n-squared in the worst case, but actually ends up being pretty good. So just to give a flavor of this, but I don't want to dwell on it too much today, is let's think about avoiding that Quicksort worst case. So as I've said, the performance of Quicksort matters a lot on who you pick as your pivots. And that affects both whether you're n log n versus n squared and your constant factors. There are other things that matter, like the actual partition strategy you pick. And there's other things you can try. And if you make bad choices, you get n-squared runtimes. And in fact, there are well-known algorithms textbooks that have accidentally made bad runtimes. Okay. So let's suppose that the pivot, so as I said, So if we suppose that the pivot always lands somewhere good, then Quicksort is n log n. But I would like to observe that those rare cases actually do happen in practice. So me just saying, well, it's rare, don't worry about it, is not supposed to keep you comfortable. For example, an array that is already in sorted order, or in almost sorted order, or an array that's all the same item, just 3, 3, 3, 3, 3, 3, the Quicksort we've described in class today will break on those types of arrays. And those are very common types of arrays. Yes, it is very special that an array is in sorted order, but it actually happens. So what I'd like you to do now is ponder what we might try to do to avoid worst case behavior. And I will give you guys a minute or so. And then I will say just a little bit more about other strategies you might try. So one person already had one suggestion. Okay. So I'm going to take a couple suggestions. Copy this stuff here. Okay, so you already had a suggestion, which is always use the median as the pivot. This works. Okay. Other suggestions you might have had? Randomly swap two indices sometimes? Oh yeah, randomly swap two indices occasionally. Oh, that's interesting. So, yeah, sporadic randomness, we'll call it. Other thoughts? Yeah. Yeah, the more hardcore version, which is shuffle before quick sorting. This definitely works and is a harder core version of the above. Okay, this definitely works with a very high probability. Other suggestions? Yeah. Partition from the center of the array. This turns out does not work. Can still find bad cases. All right, I'll take one more suggestion. Yeah. So basically, you're saying always use the median as the pivot? Yeah. Mm-hmm. Yep. Got it. I don't know if I quite processed it. Okay, sorry. But I'm happy to talk about it more. Okay, so what I'd like you guys all to do, these are all possible suggestions, and maybe ponder this a little bit. And so what I'm going to do, Friday's software engineering, I want to stick to just that on Friday. And then Monday, when we wrap up talking about other variants of Quicksort, we'll talk about what the real strategies that are used. Kind of a fun problem. Avoid that worst case behavior. All right, thank you, everybody. I'll see you Friday.